Hello there, gentle soul, and welcome to my channel, where we explore the most profound mysteries of the universe at just the right pace to help your mind unwind. Tonight, we're embarking on a quiet journey through one of the most elegant discoveries in all of physics, something so subtle that it took humanity a century to detect, yet so fundamental that it reveals the very fabric of reality itself. We're going to drift softly through the story of gravitational waves, those whispered ripples in space-time that carry messages from the most violent events in the cosmos. Think of tonight's exploration as a gentle voyage across an invisible ocean, one that surrounds us always but remained hidden until just recently, when we finally learned how to listen to its ancient songs. Now, I should warn you up front that while this video is designed to help you relax and perhaps drift towards sleep, there's always the delicate risk that the sheer wonder of what we're discussing might keep you just awake enough to marvel at the universe. But if you do find yourself still listening at the end, wide-eyed with cosmic curiosity, well, at least you'll have encountered one of the most beautiful chapters in the story of human discovery. Before we begin our journey through rippling space-time, I'd love to know where in the world you're listening from tonight, and what time it is in your corner of the universe. Are you tucked into bed in Tokyo as dawn approaches, or perhaps settling into an evening in Edinburgh with tea growing cold beside you? Whatever time zone you're calling home tonight, you're very welcome here in this quiet space we've carved out together. If you find these gentle explorations of science soothing, if they help settle your thoughts or ease you toward rest, I'd be grateful if you gave this video a like and perhaps subscribe to join our community of curious, sleepy souls. It helps more people discover these peaceful moments of wonder, and there's something lovely about knowing we're all drifting through these cosmic stories together, scattered across the globe but connected by curiosity. And as always, while we'll touch on some fascinating physics tonight, everything we discuss is for educational and relaxation purposes only, not as any form of scientific or medical advice. So let your shoulders drop, take a slow breath, and let's begin this gentle exploration of the universe's most subtle whispers. Picture, if you will, a perfectly still pond on a windless evening. The water lies like glass, reflecting the last light of sunset in perfect stillness. Now imagine dropping a single pebble into that serene surface. Watch as circles of ripples spread outward, carrying the energy of that small disturbance across the water, growing fainter as they travel but never quite disappearing, each wave a messenger, carrying news of what happened at the center. This is not a bad way to think about our universe, except the pond is not water but something far more fundamental, something Einstein called spacetime itself. And the pebbles are not small stones, but the most catastrophic events the cosmos can produce. Colliding black holes, exploding stars, the very birth cries of the universe itself. The ripples they create are gravitational waves, and for over a century, they remained as elusive as whispers in a cosmic wind. Tonight, we're going to explore how humanity finally learned to detect these ripples, what they tell us about the universe, and why their discovery represents one of the most beautiful triumphs of human ingenuity and persistence. It's a story that begins with a thought experiment by a wild-haired physicist, travels through decades of technological challenges that seemed almost impossible to overcome, and culminates in a moment when we finally heard the universe singing to us in gravitational waves. But let's start gently, as we always do, with the question that began it all. What exactly is space-time, and how can it ripple like water? To understand gravitational waves, we first need to embrace one of the most beautiful and counterintuitive ideas in all of physics, that space and time are not the fixed, unchanging backdrop against which events unfold, but rather a dynamic, flexible medium that can stretch, compress, and even vibrate like the strings of some cosmic instrument. This revelation came to us through Albert Einstein, whose general theory of relativity, published in 1915, fundamentally changed how we understand gravity itself. Before Einstein, Gravity was thought of as a force, something that reached across space to pull objects toward each other. Newton's apple falls because the Earth somehow reaches out and tugs it downward. But Einstein proposed something far more elegant and strange. In Einstein's vision, massive objects don't pull on other objects at all. Instead, they warp the very geometry of space-time around them. Imagine placing a heavy bowling ball in the center of a stretched rubber sheet. The ball creates a depression, a curve in the fabric itself. Now roll a marble across the sheet, and it will naturally follow the curved path created by the bowling ball's weight. The marble isn't being pulled by some invisible force. It's simply following the straightest possible path through curved space-time. This is gravity, according to Einstein. The Earth doesn't pull the apple downward. The Earth's mass curves space-time, and the apple simply follows that curvature. It's falling not because it's being tugged, but because it's moving along what physicists call a geodesic, the shortest path through curved space-time, much like how a ship following the curve of the Earth appears to travel in a straight line on the ocean's surface. It's a beautiful picture, isn't it? Gravity transformed from a mysterious force into geometry itself, the natural consequence of mass and energy reshaping the very fabric of reality. But Einstein's equations revealed something even more remarkable. If space-time could be curved by matter, then it could also be made to ripple, to vibrate like a drum when struck by sufficiently dramatic events. The mathematics suggested that when massive objects accelerate, particularly when they move in complex orbits around each other, they should create waves in space-time itself, disturbances that propagate outward at the speed of light, carrying energy away from the source. These gravitational waves would be incredibly subtle, stretching and compressing space itself by amounts almost impossibly small to detect. Einstein himself was uncertain whether these waves were real or merely mathematical artifacts of his equations. The effects would be so tiny, he reasoned, that they could never be measured. The universe seemed to be whispering its secrets too softly for human ears to hear. And yet, the mathematics was compelling. If two black holes were to spiral into each other, locked in an ever-tightening dance of mutual destruction, the very space-time around them would ring like a bell struck by some cosmic hammer. Waves would spread outward in all directions, carrying with them the story of that final, cataclysmic merger, that moment when two of the universe's most extreme objects became one. For decades, gravitational waves remained purely theoretical, a beautiful prediction of Einstein's equations that seemed destined to remain forever beyond our ability to detect. The challenge was almost comically daunting. These waves, even from the most violent cosmic events, would stretch space by amounts smaller than 1,000th the width of a proton. Detecting them would require measuring changes in distance that are to the width of a human hair, as a human hair is to the distance from Earth to the nearest star. It was a precision that seemed to mock human ambition, like trying to measure the thickness of a soap bubble using only a ruler made of clouds. And yet, there were those who believed it could be done. Visionaries who saw not impossibility but merely a very difficult engineering problem waiting to be solved. The story of how we finally learned to detect gravitational waves is itself a testament to human persistence and ingenuity, a decades-long journey that would require inventing new technologies, pushing the boundaries of precision measurement, and creating some of the most sensitive scientific instruments ever conceived. It begins with a concept so elegant in its simplicity that you might wonder why no one thought of it sooner. If gravitational waves stretch and compress space itself, then they should also stretch and compress any measuring devices placed in that space. Imagine two observers floating in empty space, separated by a vast distance. As a gravitational wave passes through, it would alternately stretch and compress the space between them, making their separation grow larger and smaller in a regular rhythm. The challenge, of course, is detecting these tiny changes in distance. But there is one phenomenon in nature that can measure distances with exquisite precision: light itself. Light travels at a constant speed. So if you time how long it takes for light to travel between 2 points, you can calculate the distance between them with extraordinary accuracy. And if that distance changes, even by the tiniest amount, the travel time of the light will change as well. This insight led to the concept of laser interferometry, a technique that would form the heart of gravitational wave detection. The basic idea is beautiful in its simplicity. You take a powerful laser beam and split it in two, sending the beams down two perpendicular arms of equal length. At the end of each arm, mirrors reflect the light back toward the starting point where the two beams are recombined. If the arms are exactly the same length, the light waves from each arm will arrive back at the starting point perfectly synchronized, their peaks and valleys aligned. They will constructively interfere, creating a bright spot where they recombine, but if one arm becomes even slightly longer than the other, the light waves will arrive slightly out of sync. Their peaks and valleys will be offset, and they will partially cancel each other out, creating a dimmer spot. As a gravitational wave passes through this device, it will stretch space in one direction while compressing it in the perpendicular direction. One arm will become slightly longer while the other becomes slightly shorter, and this change will be revealed by the shifting pattern of light and dark as the two laser beams interfere with each other. It sounds simple, almost elegant in its directness, but the devil, as always, lies in the details. The changes you're trying to detect are so small that they would be completely overwhelmed by vibrations from passing trucks, earthquakes on the other side of the planet, even the thermal motion of atoms in the mirrors themselves. Building a gravitational wave detector would require creating one of the quietest, most isolated environments ever constructed, a place where the cosmic whispers of spacetime could finally be heard above the noise of everyday existence. The journey to build such detectors began in the 1962nd and 72nd, led by physicists who combined visionary thinking with practical engineering skills. They had to invent new ways to isolate their instruments from vibration, develop laser systems of unprecedented stability, and create mirrors so smooth that their imperfections were measured in fractions of atoms. The mirrors themselves became marvels of precision engineering, polished to such perfection that if they were scaled up to the size of Earth, the highest mountains would be only a few feet tall. The laser systems had to maintain their frequency stability to 1 part in a trillion, a precision that makes the finest Swiss timepieces look crude by comparison. And the isolation systems, the technology designed to shield these delicate measurements from the vibrations of the world around them, became studies in the art of quietness itself. Multiple layers of suspension systems, each filtering out different frequencies of vibration, creating zones of stillness where the mirrors could hang like perfectly motionless sentinels, waiting to register the passage of gravitational waves. The scale of these detectors, too, had to be enormous. To detect the infinitesimal stretching and compressing of space, the arms of the interferometer needed to be kilometers long, creating L-shaped instruments that resembled giant tuning forks laid flat on the ground. The Laser Interferometer Gravitational Wave Observatory, or LIGO, would eventually consist of 2 such detectors, one in Louisiana and one in Washington state, each with arms 4 kilometers long, operating in perfect synchronization to distinguish gravitational waves from local disturbances. For decades, these instruments searched the sky, listening for the cosmic songs that Einstein's equations promised were there. They detected vibrations from distant earthquakes, the subtle tides raised by the moon and sun, even the infinitesimal motion caused by particles of light bouncing off their mirrors. But gravitational waves remained elusive, hiding in the noise like whispers in a crowded room. The sensitivity required was so extreme that the detectors could register disturbances caused by a person walking near the facility, by changes in atmospheric pressure, even by fluctuations in the laser light itself. Each source of noise had to be identified, understood, and either eliminated or accounted for in the analysis. It was like trying to hear a pin drop in a thunderstorm while simultaneously cataloguing every raindrop. And yet the teams of scientists and engineers working on these projects persisted, driven by the knowledge that they were attempting something unprecedented in human history, trying to open an entirely new window onto the universe. They were not just building detectors, they were creating a new sense for humanity, a way to feel the universe's most violent events as they sent ripples through the fabric of space-time itself. The story of their eventual success, and what those first detected waves revealed about the cosmos, is where our journey will continue. But for now, as we pause in this moment of anticipation, imagine the quiet dedication of those researchers, working year after year to push the boundaries of precision, to create instruments sensitive enough to register the universe's most subtle whispers. Somewhere in the darkness of space, black holes were already beginning their final spiral toward collision, already sending out the gravitational waves that would, in a few short years, announce their violent merger to anyone with ears sensitive enough to listen. The universe was singing, had always been singing, and humanity was finally, quietly, patiently learning how to hear the music. The years passed quietly in those cathedral-like halls where LIGO's detectors hummed their patient vigil, listening to the cosmos with an attention so focused it bordered on meditation. The instruments grew more sensitive with each upgrade, each refinement bringing them closer to that threshold where the universe's whispers might finally be heard above the symphony of terrestrial noise. By 2015, after decades of development and years of upgrades, the advanced LIGO detectors had achieved a sensitivity that seemed almost supernatural. They could register disturbances smaller than 1/10,000th the width of a proton, changes so minute, they challenged the very notion of what it means to measure something. The mirrors, suspended in their elaborate isolation systems, hung in a stillness so profound that they seemed to exist in a realm apart from the restless world around them. And then, on the 14th of September, 2015, at 9 hours 50 minutes and 45 seconds, Coordinated Universal Time, the universe spoke. It was a sound that had been travelling for over 1 billion years, a message launched into the cosmos long before Earth had even developed complex life, when our planet was still a world of simple cells floating in ancient seas. The signal appeared first at the LIGO detector in Livingston, Louisiana, a subtle shift in the interference pattern of laser light that lasted just 1/5 of a second. 7 milliseconds later, the same signal reached the detector in Hanford, Washington, the tiny delay confirming that something had swept across our planet at the speed of light, stretching and compressing space itself as it passed. To the human eye, there would have been nothing to see. The detectors looked exactly as they had moments before, their laser beams still splitting and recombining in their endless dance of measurement. But in the data streams flowing from those instruments, a pattern emerged that made physicists around the world hold their breath in wonder and disbelief. The signal had a distinctive shape, a rising chirp that began at low frequencies and swept upward in pitch and amplitude before abruptly cutting off. It was exactly what Einstein's equations predicted would happen when two massive objects spiral into each other, their orbital dance growing faster and more frenzied until the final moment of collision and merger. But these were not ordinary massive objects. The analysis revealed something almost beyond comprehension. Somewhere in the southern sky, approximately 1.3 billion light-years away, two black holes had been locked in their final embrace. One had a mass about 36 times that of our Sun, the other about 29 times. For perhaps millions of years, they had been spiraling closer together, their gravitational dance gradually shrinking as energy was carried away by gravitational waves too faint for our instruments to detect. But in those final moments, as the two black holes approached each other at significant fractions of the speed of light, the waves they generated grew stronger and stronger. The frequency of their orbital dance increased, like a cosmic drum roll building to its crescendo. And then, in a collision that released more energy in gravitational waves than all the stars in the observable universe emit in light, the two became one. For just a few milliseconds, that collision generated gravitational waves with a peak power output 50 times greater than the total light output of all the stars and galaxies in the observable universe combined. It was a release of energy so vast that it defies comfortable comprehension, yet it reached us as the most delicate of whispers, a barely perceptible stretching and compressing of space that required humanity's most sensitive instruments to detect. The final merged black hole had a mass about 62 times that of the Sunday. Simple arithmetic reveals something profound about this event. The two original black holes had masses that added up to 65 solar masses, but the final black hole contained only 62. 3 entire solar masses had been converted into pure gravitational wave energy and radiated away into space. In those brief moments of collision, mass itself had been transformed into the ripples of spacetime that eventually reached our detectors. It was Einstein's famous equation, E equals mc squared, played out on the grandest possible stage. Matter had become energy, energy had become the curvature of spacetime itself, and that curvature had propagated across 1 billion light-years to gently nudge the mirrors in our detectors by less than the width of a proton. The discovery team spent months analyzing the data, checking and rechecking their results, searching for any possible source of error or contamination. The signal was so clear, so perfectly matched to theoretical predictions, that it almost seemed too good to be true. Could some terrestrial disturbance have created such a pattern? Could it be an elaborate hoax, a test signal injected into the system? But the evidence was overwhelming. The signal appeared in both detectors with the proper time delay for a gravitational wave traveling at light speed. Its frequency evolution matched Einstein's predictions with extraordinary precision. Most convincingly, the signal contained information that no terrestrial source could have produced, details about the masses and spins of the colliding black holes that emerged naturally from the gravitational wave analysis. On the 11th of February 2016, at a press conference that made headlines around the world, the LIGO collaboration announced that gravitational waves had been detected for the first time. It was a moment that marked not just a scientific triumph, but the birth of an entirely new field of astronomy. For the first time in human history, we had observed the universe not through electromagnetic radiation, light in all its forms, but through the direct detection of space-time distortions. The implications were profound and beautiful. Gravitational waves carry information that light cannot. They emerge from regions of space-time, so warped that light itself cannot escape, from the event horizons of black holes and the cores of colliding neutron stars. They travel through the universe largely unimpeded, passing through matter as if it weren't there, carrying pristine information about the most extreme events in cosmic history. With this first detection, we had opened what scientists called a new window on the universe. It was as if humanity, after eons of being deaf to a vast symphony of cosmic events, had suddenly gained the ability to hear. The universe had been filled with gravitational wave sources all along, black hole mergers and neutron star collisions, the birth cries of the early cosmos itself, but we had been living in silence, unaware of the songs surrounding us. The detected signal, catalogued as G150,000, 914-inch honor of its discovery date, became the first entry in what would grow into a catalogue of gravitational wave events. Each detection would add to our understanding of the universe's most extreme phenomena, revealing populations of black holes we never knew existed, providing new tests of Einstein's theory, and offering insights into the fundamental nature of gravity itself. But beyond the scientific implications, there was something deeply moving about this achievement. It represented the culmination of human curiosity and ingenuity, a century-long journey from Einstein's theoretical insights to the moment when we finally heard the universe singing to us in gravitational waves. It showed that no challenge is too great for human persistence, that even the most impossible-seeming measurements can be achieved with enough dedication and cleverness. The detection also revealed something beautiful about the nature of scientific collaboration. The LIGO project involved more than 1,000 scientists and engineers from institutions around the world, working together for decades to achieve a goal that no individual or small team could have accomplished alone. It was science at its most collaborative and international, a reminder that our greatest achievements often come when we work together toward common goals. In the months and years following that first detection, more gravitational wave events would be discovered, each adding new chapters to our understanding of the cosmos. Binary black hole mergers became routine detections, each one revealing new details about how these extreme objects form and evolve. The merger of two neutron stars, detected in both gravitational waves and light, would open up the field of multi-messenger astronomy and solve decades-old puzzles about the origin of heavy elements. But perhaps most remarkably, each new detection confirmed Einstein's century-old predictions with stunning accuracy. The general theory of relativity, conceived in the mind of a physicist working with nothing more than pencil, paper, and profound insight, continued to describe the behavior of space-time under the most extreme conditions the universe could provide. It was a testament to the power of human reason and mathematical insight to reveal the deepest truths about reality. As we pause here in our gentle exploration, drifting through this story of cosmic discovery, consider the patience and dedication of those who made this achievement possible. For decades, they worked toward a goal that many thought impossible, driven by nothing more than curiosity about the fundamental nature of our universe. They created instruments of unprecedented precision, solved engineering challenges that seemed insurmountable, and ultimately gave humanity a new sense with which to explore the cosmos. Somewhere in the darkness tonight, more gravitational waves are washing over us, carrying stories of distant cosmic violence that we are only beginning to learn how to read. Black holes are spiraling toward collision. Neutron stars are dancing their final dance, and the universe itself may still be ringing with echoes of its violent birth. We are surrounded by this invisible ocean of space-time distortions, these whispers from the most extreme corners of reality, and we have finally learned how to listen. The story continues. As new detectors come online and our sensitivity improves, as we learn to hear fainter and more distant sources, as we begin to map the gravitational wave sky with the same care and attention that astronomers have long devoted to the sky of light. We are still in the early days of gravitational wave astronomy, still learning the language of these cosmic ripples, still discovering what secrets they carry about the nature of space and time themselves. The gentle hum of discovery continued to resonate through the halls of physics laboratories around the world as more gravitational wave detectors joined this cosmic chorus. In Italy, the Virgo detector added its voice to the symphony, and later KAGRA in Japan would contribute its own sensitive ear to this growing network of listeners. Each new detector brought improved precision and, more importantly, the ability to triangulate the sources of these cosmic whispers with greater accuracy. Think of it like trying to locate the source of a distant sound in a vast, dark landscape. With one ear, you might hear the sound but struggle to determine its direction. With two ears, you begin to develop a sense of where it might be coming from. But with 3 or 4 listeners scattered across the globe, you can pinpoint the source with remarkable precision, painting coordinates in the sky where telescopes might look for the light that sometimes accompanies these gravitational wave events. This network approach revealed something beautiful about the collaborative nature of modern astronomy. The detectors, separated by thousands of kilometers, work together in perfect synchronization, their data streams combined and analyzed as if they were components of a single planet-sized instrument. It's a testament to human cooperation on a global scale, nations working together to listen for the universe's most subtle messages. As the catalogue of detections grew, patterns began to emerge from the data that surprised even the most optimistic researchers. The universe, it seemed, was far more violent and dynamic than anyone had imagined. Black hole mergers were happening with startling frequency, suggesting that these cosmic monsters were far more common than previous observations had indicated. Each detection revealed binary systems with masses and properties that challenged existing theories about how such objects form and evolve. Some of the detected black holes were surprisingly massive, far heavier than any stellar remnant should be according to conventional stellar evolution models. Others spun at rates that approached the theoretical maximum, whirling through space like cosmic tops spinning at the very edge of stability. The diversity of these systems painted a picture of a universe filled with gravitational laboratories, natural experiments in extreme physics playing out across cosmic time. But perhaps the most profound revelation came not from any single detection, but from the cumulative weight of all these observations. Each gravitational wave event represented a direct measurement of spacetime curvature, a test of Einstein's theory under conditions more extreme than anything that could be replicated in any earthly laboratory. And time after time, the predictions of general relativity proved correct to extraordinary precision. The waves arrived at precisely the times predicted by Einstein's equations. Their frequency evolution followed the mathematical curves derived from first principles over a century ago. The energy radiated away matched the theoretical calculations with an accuracy that bordered on the supernatural. It was as if Einstein himself had been present at these cosmic collisions, taking notes and confirming that yes, this is exactly how spacetime should behave under such extreme circumstances. This validation of general relativity opened new avenues for understanding the fundamental nature of gravity itself. Gravitational waves provided a unique probe of spacetime in the strong field regime, where Newton's approximations break down completely and only Einstein's full theory can describe what happens. They offered tests of whether gravity behaves as predicted when spacetime is stretched and twisted to its very limits. Some of the most intriguing detections came from events that pushed the boundaries of what we thought possible. Ultramassive black hole mergers that radiated gravitational wave energy equivalent to the mass energy of several suns. Systems where the two objects had very different masses, creating asymmetric collisions that generated waves with complex polarization patterns. Each event added new data points to our understanding of how gravity behaves in its most extreme manifestations. The precision of these measurements also allowed physicists to search for deviations from Einstein's predictions, subtle signs that general relativity might not be the complete story of gravity. They looked for extrapolarization modes that some alternative theories predicted, for violations of the speed limit that says gravitational waves should travel at exactly the speed of light, for signatures of extra dimensions or exotic forms of matter. So far, Einstein's theory has passed every test with flying colours, but the search continues with each new detection. One of the most remarkable aspects of gravitational wave astronomy is how it has revealed the universe's hidden populations. Before these detections, astronomers had identified only a handful of stellar mass black holes in our galaxy, mostly through their gravitational effects on companion stars. But gravitational wave observations have revealed that such objects are far more numerous than anyone suspected, with binary black hole systems scattered throughout the cosmos, most of them completely invisible to traditional telescopes. This discovery has profound implications for our understanding of stellar evolution and cosmic history. It suggests that massive stars commonly end their lives by collapsing into black holes, and that these black holes often exist in binary pairs that eventually spiral together and merge. The rate of such mergers implies a universe filled with these dark, massive objects, contributing significantly to the total mass budget of the cosmos. The detectors have also observed events that bridge the gap between different astronomical phenomena. Some gravitational wave sources appear to be intermediate mass black holes, objects that fill the mysterious gap between stellar mass black holes and the supermassive black holes found at the centers of galaxies. Others might represent the collision of a black hole with a neutron star, creating hybrid systems that help us understand the relationship between these two most extreme forms of matter. Perhaps most tantalizingly, some signals have been detected that don't fit neatly into any existing category. These events, still being analyzed and debated, might represent entirely new types of astrophysical phenomena, cosmic processes that we haven't yet learned to recognize or understand. They remind us that we are still in the early days of gravitational wave astronomy, still discovering what kinds of messages the universe has been sending us all along. The technology behind these detections continues to evolve and improve. New techniques for isolating the detectors from environmental noise, more powerful lasers, better mirror coatings, and sophisticated data analysis methods all contribute to increasing sensitivity. Each improvement allows us to see farther into space and deeper into cosmic time, detecting weaker signals from more distant events. Future upgrades promise even greater sensitivity, potentially allowing us to detect gravitational waves from sources that existed when the universe was a fraction of its current age. Some proposed space-based detectors would use laser interferometry on scales of millions of kilometers, creating instruments sensitive to gravitational waves from supermassive black hole mergers at the centers of distant galaxies. These technological advances are complemented by increasingly sophisticated theoretical work. Computer simulations of black hole mergers now achieve unprecedented accuracy, modeling the complex dynamics of spacetime itself as it responds to the motion of these extreme objects. The simulations reveal the intricate choreography of the final moments before collision, when two black holes circle each other at significant fractions of light speed, their event horizons beginning to distort and stretch, before finally touching and merging into a single, larger whole. The computational challenges involved in these simulations are staggering. They require solving Einstein's equations in their full nonlinear glory, tracking how space-time curvature evolves as massive objects accelerate through it. The mathematics is so complex that it pushes supercomputers to their limits, requiring months of processing time to model just the final few seconds of a billion-year cosmic dance. But the rewards are equally remarkable. These simulations provide the theoretical templates that allow us to extract maximum information from gravitational wave detections. By comparing observed signals with calculated waveforms, we can determine not just the masses of the merging objects, but their spins, their orbital orientations, and even details about how their event horizons behave during the collision. The merger process itself reveals physics that exists nowhere else in the universe. In those final moments, as two black holes approach each other, their individual event horizons begin to distort, stretching toward each other like cosmic teardrops. The region between them becomes a zone of space-time so violently curved that our normal concepts of space and time begin to break down. When the horizons finally touch, they immediately snap into a new unified shape, but this new black hole is far from calm. Its event horizon writhes and oscillates like the surface of a struck bell, gradually settling into the smooth spherical shape that characterizes a black hole in equilibrium. These oscillations, called quasinormal modes, ring out in gravitational waves with frequencies and decay times that depend only on the mass and spin of the final black hole. Detecting and analyzing these ring-down phases provides yet another test of general relativity, confirming that black holes behave exactly as Einstein's theory predicts. The mathematics that describes these oscillations was worked out decades before we had any hope of observing them, yet the detections match the predictions with extraordinary precision. As our catalogue of gravitational wave events continues to grow, astronomers are beginning to use these detections to probe fundamental questions about the nature of the universe itself. The way gravitational waves propagate across cosmic distances provides new ways to measure the expansion rate of the universe. potentially resolving discrepancies that have puzzled cosmologists for years. Gravitational waves also offer unique insights into the equation of state of neutron star matter, the relationship between pressure and density in material compressed to nuclear density and beyond. When neutron stars merge, the gravitational waves they emit carry information about how this exotic matter behaves under the most extreme conditions imaginable. These observations are revealing that neutron stars are even stranger than we thought. The matter in their cores may exist in phases that don't occur anywhere else in the universe, with quarks and gluons existing in configurations that can only be studied through their gravitational wave signatures. Each neutron star merger becomes a cosmic laboratory experiment, probing physics that we could never hope to replicate on Earth. The field of gravitational wave astronomy is also beginning to explore the possibility of detecting much fainter, more persistent sources. While the dramatic mergers of black holes and neutron stars create brief, powerful bursts of gravitational waves, the universe may also be filled with continuous sources that generate much weaker but steady signals. Rapidly spinning neutron stars with even tiny asymmetries in their shape should emit gravitational waves continuously as they rotate, like cosmic lighthouses beaming their signals across space. Detecting these persistent sources requires different analysis techniques, searching for patterns that persist over months or years, rather than the fraction of a second typical of merger events. There's also the tantalizing possibility of detecting gravitational waves from the early universe itself, primordial signals that might carry information about cosmic inflation, the rapid expansion that shaped the universe in its first fraction of a second. These waves, if they exist and can be detected, would provide a direct probe of physics at energy scales far beyond anything achievable in particle accelerators. The story of gravitational waves is still being written, with each new detection adding chapters to our understanding of the cosmos. We are witnessing the birth of a new form of astronomy, one that uses the fabric of spacetime itself as a detection medium, listening for the songs that the universe's most extreme objects have been singing across cosmic time. As you drift towards sleep tonight, perhaps carried along by these gentle currents of cosmic discovery, remember that you exist within this ocean of gravitational waves, these ripples in space-time that connect you to the most distant and ancient events in cosmic history. The merger that created the waves detected by LIGO happened when our planet was young, and life was just beginning to explore the possibilities of complexity. Those waves traveled across 1 billion years of cosmic history to reach us, carrying their message through the rise and fall of countless stars, through the formation of galaxies and the evolution of life itself. They passed through our solar system, through the Earth, and through your own body, stretching and compressing space by amounts so small that even our most sensitive instruments can barely detect them. Yet, in that detection lies something profound about the human spirit, our endless curiosity about the universe and our place within it. We have learned to listen for whispers so faint they barely disturb the quantum foam of spacetime itself, and in doing so, we have gained a new sense with which to explore the cosmos. The universe continues to sing to us in gravitational waves, sharing stories of cosmic violence and beauty that span the breadth of space and the depth of time. Each ripple carries with it the memory of cataclysmic events, the final moments of stellar giants, the birth cries of black holes, and perhaps even echoes of the universe's own creation. And we, in our quiet corners of this vast cosmos, have learned to hear these ancient songs, adding our own small voice to the symphony of discovery that defines the human experience. The waves that Einstein predicted in the silence of his study have become humanity's newest window into the infinite, carrying us ever deeper into the mystery and wonder of the universe we call home. Tonight, as you settle into the gentle rhythm of this cosmic story, let us drift towards something even more remarkable than the detection of gravitational waves themselves. For in learning to hear these whispers from space, we have not merely confirmed Einstein's century-old predictions, We have opened a door to understanding the universe in ways that were previously unimaginable. Consider, if you will, the profound shift that gravitational wave astronomy represents in how we explore the cosmos. For thousands of years, humans looked up at the night sky and saw only light electromagnetic radiation in all its forms, from the gentle glow of starlight to the fierce radiation of distant quasars. Our telescopes, no matter how sophisticated, were essentially elaborate eyes, gathering and focusing light to reveal the universe's secrets. But light, for all its beauty and utility, has limitations. It can be absorbed by dust clouds, scattered by gas, blocked entirely by dense matter. There are regions of the universe that remain forever hidden from our optical telescopes, shrouded in darkness not because they lack energy or activity, but because their light cannot reach us through the maze of cosmic matter. Gravitational waves, however, travel through the universe largely unimpeded. They pass through planets and stars, through galaxies and nebulae, as if these massive objects were mere phantoms. A gravitational wave that began its journey at the moment two black holes merged will arrive at Earth carrying the same information it started with, unmarked by its passage through the cosmic web of matter and energy. This transparency gives gravitational wave astronomy a unique power to peer into the universe's most hidden corners. When we detect the waves from a black hole merger, we are observing that event almost exactly as it happened, unfiltered by the intervening billions of years and trillions of miles. It's as if we have developed X-ray vision for the cosmos, able to see through the universe's accumulated dust and gas, to witness events that would otherwise remain forever invisible. The implications of this new transparency are still being explored, but they promise to revolutionize our understanding of cosmic history. We may be able to trace the evolution of black holes back to the universe's earliest epochs, to understand how the first massive stars lived and died, to map the distribution of dark matter through its gravitational influence on these cosmic collisions. Each gravitational wave detection also provides us with a new kind of cosmic ruler, a way to measure distances across the universe that doesn't depend on the traditional ladder of stellar observations. When two massive objects merge, the strength of the gravitational waves they produce depends directly on how far away they are. By measuring both the amplitude of the waves and the properties of the merging objects, we can calculate their distance with remarkable precision. This technique, known as the standard siren method, offers an independent way to measure the expansion rate of the universe, potentially resolving long-standing debates about cosmic distances and the nature of dark energy. It's particularly powerful when combined with optical observations of the same event, creating what astronomers call multi-messenger astronomy. The most spectacular example of this multi-messenger approach came in August 2017, when the LIGO and Virgo detectors observed gravitational waves from the merger of two neutron stars. Unlike black hole mergers, which typically produce no visible light, this collision was accompanied by a brilliant explosion that lit up telescopes across the electromagnetic spectrum. Within seconds of the gravitational wave detection, alerts went out to observatories around the world. Telescopes swiveled to point toward the region of sky where the merger had occurred, and what they found was extraordinary. A kilonova, a type of explosion that had been theoretical until that moment, blazed forth in precisely the location predicted by the gravitational wave analysis. The light from this event told a story that complemented the gravitational wave detection beautifully. While the waves revealed the final moments of the neutron star merger, the optical observations showed what happened afterward, as the debris from the collision expanded outward in a cloud of newly created heavy elements. This single event solved several long-standing puzzles in astronomy. It confirmed that neutron star mergers are indeed the primary source of many heavy elements in the universe, the cosmic forges where gold, platinum, and other precious metals are created. The gold in your jewelry, the silver in your electronics, may well have been forged in just such a collision billions of years ago, scattered into space by the explosive aftermath of two neutron stars' final dance. The multi-messenger observation also provided new insights into the nature of gamma-ray bursts, those mysterious flashes of high-energy radiation that had puzzled astronomers for decades. The neutron star merger was accompanied by a gamma-ray burst, confirming theoretical predictions about the connection between these phenomena. Perhaps most remarkably, the combined gravitational wave and optical observations provided a completely new way to measure the expansion rate of the universe. By comparing the distance measured from gravitational waves with the recession velocity measured from the optical spectrum, astronomers could calculate the Hubble constant, the parameter that describes how fast the universe is expanding. This measurement, independent of all previous methods, has the potential to resolve a growing tension in cosmology. Different techniques for measuring cosmic expansion have been giving slightly different answers, a discrepancy that has puzzled cosmologists and might hint at new physics beyond our current understanding. Gravitational wave standard sirens offer a fresh perspective on this puzzle, a way to measure cosmic distances that doesn't rely on the traditional chain of stellar observations. As the network of gravitational wave detectors continues to grow and improve, these multi-messenger events are expected to become more common. Each one will add to our understanding of how the universe works, providing new tests of fundamental physics and new insights into the cosmic processes that shape the cosmos around us. The detectors themselves continue to evolve, pushing ever closer to the theoretical limits of precision measurement. Each upgrade brings increased sensitivity, allowing us to hear fainter signals from more distant sources, to peer deeper into cosmic history and farther across space. Future generations of gravitational wave observatories will extend our reach even further. Space-based detectors, free from the vibrations and limitations of earthbound instruments, will open up entirely new frequency ranges of gravitational waves. These space interferometers will be sensitive to waves from supermassive black hole mergers at the centers of distant galaxies, events so energetic they can be detected across cosmic time. The European Space Agency's LIGO mission, planned for launch in the 2032, will create a gravitational wave detector with arms millions of kilometers long, using 3 spacecraft flying in precise formation as they orbit the Sunday. This space-based observatory will be sensitive to gravitational waves with much lower frequencies than ground-based detectors can observe, opening up an entirely new window on the cosmos. LIGO will be able to detect the gravitational waves from supermassive black holes as they spiral toward merger over periods of years or even decades. Instead of the brief chirps that characterize stellar mass black hole collisions, these events will create long, evolving songs that we can follow from their earliest whispers to their final, catastrophic crescendo. These observations will provide unprecedented insights into how galaxies form and evolve, how supermassive black holes grow and interact, and how the largest structures in the universe are assembled over cosmic time. We will be able to map the population of massive black holes throughout the cosmos, tracing their history back to the universe's youth when the first galaxies were just beginning to form. But perhaps the most tantalizing possibility offered by gravitational wave astronomy is the prospect of detecting signals from the universe's earliest moments. If cosmic inflation, the rapid expansion that shaped the universe in its first tiny fraction of a second, generated gravitational waves, as theory suggests, those primordial ripples might still be propagating through space today. Detecting these primordial gravitational waves would provide direct evidence for inflation, confirming one of the most important theories in modern cosmology. More than that, it would give us a window into the universe when it was less than a trillionth of a trillionth of a trillionth of a second old, allowing us to probe physics at energy scales that can never be reached by any conceivable particle accelerator. These ancient waves would carry information about the fundamental forces of nature as they existed in the universe's first moments, about the quantum fluctuations that eventually grew into the galaxies and stars we see today, about the very birth of space and time themselves. The search for primordial gravitational waves represents the ultimate goal of gravitational wave astronomy, the possibility of detecting echoes from the universe's creation itself. It would be the cosmic equivalent of hearing the first cry of a newborn, the initial sound of existence announcing itself to an empty cosmos. As our detectors grow more sensitive and our analysis techniques more sophisticated, we edge closer to this extraordinary possibility. Each improvement in technology, each refinement in data processing, brings us nearer to the moment when we might finally hear the universe's birth song, preserved in the fabric of space-time itself. The journey from Einstein's theoretical insight to the detection of gravitational waves spans a full century of human effort, creativity, and persistence. It represents one of the greatest intellectual achievements in human history, comparable to the development of quantum mechanics or the discovery of the structure of DNA. But perhaps, more than any specific discovery, gravitational wave astronomy represents something profound about the human spirit itself. It shows that there are no limits to human curiosity, no challenges too great for our ingenuity to overcome, no whispers from the cosmos too faint for us to eventually hear. The scientists and engineers who built these detectors worked for decades on a project that many thought impossible, driven by nothing more than the desire to understand the universe a little better. They created instruments of unprecedented precision, solved engineering problems that seemed insurmountable, and ultimately gave humanity a new sense with which to explore the cosmos. Their success reminds us that the most important discoveries often require the longest journeys, that the universe's deepest secrets are revealed not to those who seek quick answers, but to those who are willing to spend lifetimes listening for the faintest of signals. As you rest tonight, carried along by these gentle currents of discovery, remember that you are living through one of the most remarkable periods in the history of human knowledge. We are the first generation to hear gravitational waves, the first to witness black holes colliding, the first to experience the universe not just through light, but through the direct detection of spacetime's vibrations. Somewhere in the darkness above, more gravitational waves are washing over our planet, carrying stories of cosmic violence and beauty that we are only beginning to learn how to read. Each ripple in spacetime connects us to events of unimaginable power and scale, reminding us that we are part of a universe far stranger and more wonderful than our ancestors could have imagined. The waves continue their ancient journey across the cosmos, as they have for billions of years, as they will for billions more. But now, for the first time in cosmic history, there are listeners on a small planet orbiting an ordinary star, beings who have learned to hear the universe's songs and to find in them new chapters in the endless story of existence itself. The gentle story of gravitational waves carries us now towards something even more profound and quietly revolutionary. As we settle deeper into this cosmic narrative, let us explore how these ripples in space-time are beginning to reveal not just individual events, but the very architecture of the universe itself, painted in vibrations we are only now learning to perceive. Imagine, if you will, that you've spent your entire life in a world without sound, where all information comes to you through sight alone. You understand your surroundings through light and shadow, color and movement, but the rich tapestry of audio remains completely unknown. Then, suddenly, you develop the ability to hear. The world doesn't just become more complete, it becomes fundamentally different. Sounds reveal hidden activities, distant events, the subtle communications of life itself. This is precisely what has happened to astronomy with the advent of gravitational wave detection. We are experiencing the cosmic equivalent of gaining a new sense. And like any profound sensory expansion, it is revealing aspects of reality that were not just hidden, but literally unimaginable before. The universe, it turns out, is far more dynamic and alive than our light-based observations had suggested. Each gravitational wave detection represents not just a single event, but a data point in an emerging map of cosmic activity that spans scales from stellar remnants to the largest structures in the universe. We are beginning to see patterns in this activity, rhythms and relationships that speak to deeper organizing principles in cosmic evolution. Consider the population of black holes that gravitational wave astronomy has revealed. Before these detections, our knowledge of stellar mass black holes came primarily from X-ray observations of systems where a black hole was stealing matter from a companion star. These accretion-powered sources gave us a limited and biased sample, showing us only black holes that happen to be actively feeding and thus producing detectable radiation. Gravitational waves, by contrast, reveal black holes in their most natural state, as isolated objects or binary pairs that produce no electromagnetic signature whatsoever. The population that has emerged from these observations is strikingly different from what we expected. Black holes appear to be more massive on average, more numerous, and more likely to exist in binary systems than previous studies had suggested. This discovery has profound implications for our understanding of stellar evolution, the processes by which massive stars live and die. The gravitational wave detections suggest that a significant fraction of the most massive stars end their lives not in spectacular supernova explosions that leave behind neutron stars, but in more subtle collapse events that create black holes directly. These so-called failed supernovae may be one of the primary pathways for black hole formation, a process that remains largely invisible to traditional astronomical observations. The binary nature of many detected systems also tells us something important about how massive stars evolve in pairs. The orbital dance that brings two black holes together over cosmic time is delicate and complex, requiring the binary system to survive multiple phases of stellar evolution, including episodes where one or both stars swell to enormous sizes and shed vast amounts of mass into space. Some of these evolutionary pathways involve phases where the two massive stars are so close together that they share a common envelope of gas, spiraling together through their own stellar atmospheres in a process that either brings them closer together or tears the binary apart entirely. The fact that we detect so many black hole mergers suggests that nature has found ways to navigate these treacherous evolutionary phases, producing binary systems that can survive long enough to eventually merge. The timing of these mergers also reveals something beautiful about cosmic patience. The black hole binaries we detect today formed from massive stars that lived and died billions of years ago. After their parent stars collapsed into black holes, these systems spent eons slowly spiraling inward, their orbits shrinking at a rate so gradual that the merger occurs only after times comparable to the current age of the universe. This means that the gravitational wave events we detect today are, in a very real sense, fossils from the universe's youth. They carry information about star formation and stellar evolution from epochs when the cosmos was fundamentally different from what we see today, when the first generation of massive stars was just beginning to explore the possibilities of nuclear fusion. Each detection thus becomes a kind of cosmic archaeology, revealing not just the properties of the merging objects themselves, but the conditions that existed when those objects first formed. The mass distribution of detected black holes provides clues about the initial mass function of stars in the early universe. The rate of mergers tells us about the efficiency of binary evolution pathways. Even the spins of the black holes carry information about how they formed and whether they have grown through subsequent accretion or mergers. As our catalogue of detections continues to expand, astronomers are beginning to use these observations to trace the cosmic history of star formation itself. The rate of black hole mergers as a function of distance, and thus cosmic time, provides a direct probe of when and where massive stars were forming throughout the universe's history. This gravitational wave view of cosmic history is revealing surprises. The merger rate appears to peak at intermediate redshifts, corresponding to times when the universe was roughly half its current age. This peak coincides with the epoch when star formation throughout the universe was at its most vigorous, suggesting a direct connection between the formation of massive stars and the black hole mergers we observe today. But gravitational waves are teaching us about more than just black holes and neutron stars. They are beginning to reveal fundamental properties of space-time itself, providing tests of Einstein's theory under conditions more extreme than anything we could hope to create in terrestrial laboratories. Each detected gravitational wave carries with it information about how space-time behaves when it is stretched and compressed to its very limits. The precise timing of wave arrivals at different detectors tests whether gravitational disturbances really do propagate at the speed of light. The polarization patterns of the waves probe whether spacetime has the geometric properties that Einstein predicted. The way waves interact with matter as they pass through the Earth tests our understanding of how gravity couples to different forms of energy and momentum. So far, every test has confirmed Einstein's predictions with remarkable precision. Gravitational waves arrive at exactly the speed of light. They carry exactly the polarization patterns predicted by general relativity. They interact with matter in precisely the ways that Einstein's equations demand. The theory that emerged from the mind of a single physicist, working with nothing more than mathematical insight and physical intuition, continues to describe reality with an accuracy that borders on the uncanny. But this remarkable agreement between theory and observation does more than just validate Einstein's work. It provides us with confidence that we truly understand how gravity behaves under the most extreme conditions, opening the door to using gravitational waves as probes of even more exotic phenomena. Some of the most intriguing possibilities involve using gravitational wave observations to search for signatures of physics beyond Einstein's theory. While general relativity has passed every test so far, there are theoretical reasons to expect that it might be incomplete, that new physics might emerge at the highest energies and strongest gravitational fields. Alternative theories of gravity make subtle predictions that differ from Einstein's, in ways that might be detectable with sufficiently sensitive gravitational wave observations. Some predict additional polarization modes that would create distinctive signatures in the detector data. Others suggest that gravitational waves might not travel at exactly the speed of light, or that they might interact with exotic forms of matter in ways that Einstein's theory doesn't allow. The search for these subtle deviations represents one of the most exciting frontiers in gravitational wave science. Each new detection provides another opportunity to test the foundations of our understanding, to push the boundaries of known physics, to search for clues that might point toward a more complete theory of gravity and space-time. There's something almost poetic about using the universe's most violent events to probe its most subtle properties. The cataclysmic collisions of black holes, events of unimaginable violence and energy, become delicate instruments for measuring the fine structure of physical law. In the brief moments when space-time itself rings like a struck bell, we find opportunities to test our deepest theories about the nature of reality. This interplay between the cosmic and the fundamental reflects a broader theme in modern physics, the recognition that the universe itself serves as our ultimate laboratory. The conditions that exist in the cores of neutron stars, in the vicinity of black hole event horizons, during the first moments after the Big Bang, can never be replicated on Earth. But nature provides these extreme environments naturally, and gravitational waves give us a way to study them directly. Each gravitational wave detection is thus both an astronomical observation and a fundamental physics experiment. We are simultaneously mapping the population of compact objects in the universe and probing the behavior of space-time under the most extreme conditions imaginable. It's a beautiful synthesis of observational astronomy and theoretical physics, each discipline informing and enriching the other. The technological challenges involved in these observations continue to push the boundaries of precision measurement. The current generation of detectors has already achieved sensitivities that seemed impossible just a few decades ago, but the quest for even greater precision continues. Each improvement in sensitivity opens up new regions of parameter space, allowing us to detect weaker signals from more distant sources, to probe deeper into cosmic history. Future detector upgrades will push these capabilities even further. The next generation of ground-based instruments will be 10 times more sensitive than current detectors, allowing them to observe black hole mergers out to cosmological distances. These observations will provide a three-dimensional map of the universe's structure as revealed by gravitational waves, complementing and extending the maps created by galaxy surveys and other traditional astronomical techniques. The engineering challenges involved in achieving these sensitivities are extraordinary. Every component of the detector must be optimized for maximum precision, from the laser systems that provide the measuring light to the suspension systems that isolate the mirrors from environmental vibrations. The mirrors themselves must be polished to atomic smoothness. The vacuum systems must remove virtually every molecule of air from the detector arms, and the data analysis systems must be capable of extracting signals buried in noise thousands of times stronger than the signal itself. Perhaps most remarkably, these instruments must be stable enough to maintain their sensitivity for months or years at a time. Unlike many scientific instruments that make brief measurements under carefully controlled conditions, gravitational wave detectors must operate continuously, always ready to capture the next cosmic event. They are monuments to human patience and persistence, technological marvels that embody our commitment to listening for the universe's faintest whispers. The global network of these detectors represents one of the most ambitious international scientific collaborations ever undertaken. Scientists and engineers from dozens of countries work together to design, build, and operate these instruments, sharing data and expertise across national boundaries in pursuit of common scientific goals. It's a testament to the unifying power of curiosity, to our shared desire to understand the cosmos we inhabit. This collaborative spirit extends beyond the gravitational wave community itself. The detection of each new event triggers a cascade of follow-up observations across the electromagnetic spectrum, as telescopes around the world search for optical counterparts to the gravitational wave sources. This multi-messenger approach, combining gravitational waves with traditional astronomical observations, is revealing aspects of cosmic phenomena that neither technique could uncover alone. The rapid response required for these follow-up observations has revolutionized astronomical practice. Within seconds of a gravitational wave detection, automated systems alert observatories around the world, providing sky coordinates where the source might be visible. Telescopes respond with unprecedented speed, some beginning their searches within minutes of the initial alert. This real-time approach to astronomy represents a fundamental shift in how we study the universe. Instead of planned observations of known objects, we now have the capability to respond immediately to cosmic events as they unfold, capturing phenomena in their earliest moments when they are often at their most revealing. The success of this approach was demonstrated dramatically during the neutron star merger, observed in 2017. Within hours of the gravitational wave detection, telescopes across the globe had identified the optical counterpart, beginning a weeks-long campaign of observations that tracked the evolution of the kilonova explosion in unprecedented detail. These coordinated observations revealed the complex physics of neutron star mergers, from the initial collision that created the gravitational waves to the radioactive decay of newly synthesized heavy elements that powered the optical emission. It was a masterclass in multi-messenger astronomy, showing how different types of observations can work together to create a complete picture of cosmic phenomena. As we continue to develop our gravitational wave capabilities, the potential for even more dramatic discoveries grows. Each improvement in detector sensitivity, each new detector added to the global network, each advance in data analysis techniques brings us closer to detecting signals that could revolutionize our understanding of the universe. The possibility of detecting continuous gravitational waves from rapidly spinning neutron stars represents one such frontier. These signals would be much weaker than the brief bursts from merging objects, but they would provide unprecedented insights into the structure and composition of matter under extreme conditions. By studying how these signals change over time, we could learn about the internal physics of neutron stars, about how matter behaves when compressed to densities that exceed those found in atomic nuclei. The search for stochastic gravitational wave backgrounds represents another exciting possibility. These would be signals created not by individual sources, but by the superposition of many weak sources throughout the universe, creating a kind of gravitational wave static that permeates all of space. Detecting this background would provide information about the collective population of gravitational wave sources, about the history of compact object formation throughout cosmic time. Most tantalizingly, there remains the possibility of detecting primordial gravitational waves from the earliest moments of the universe itself. These signals, if they exist and can be detected, would provide direct information about the physics of cosmic inflation, about the quantum fluctuations that eventually grew into the large-scale structure we see today. The technical challenges involved in detecting these faint, ancient signals are enormous. They would be buried beneath the noise from countless other sources, requiring analysis techniques of unprecedented sophistication and detector sensitivities that push against the fundamental limits imposed by quantum mechanics itself. Yet the potential rewards are equally extraordinary. Primordial gravitational waves would give us a window into the universe when it was less than a trillionth of a trillionth of a trillionth of a second old, allowing us to study physics at energy scales that can never be reached by any earthly experiment. They would provide direct evidence for cosmic inflation, confirming one of the most important theories in modern cosmology. More than that, they would represent the ultimate triumph of human curiosity and ingenuity, the detection of signals so ancient and faint that they challenge our very conception of what it means to observe the universe. They would be echoes from the birth of space and time themselves, preserved in the fabric of reality, and finally heard by creatures who evolved billions of years later on a small planet orbiting an ordinary star. As you drift gently towards sleep tonight, carried along by these currents of cosmic discovery, consider the extraordinary journey that gravitational wave astronomy represents. From Einstein's theoretical insight to the first detection, from those early observations to the rich science emerging today, it exemplifies everything that is most beautiful about human curiosity and creativity. We have learned to hear the universe singing to us in gravitational waves, and in doing so, we have opened a new chapter in the long story of human exploration and discovery. Each ripple in space-time connects us to events of cosmic significance, reminding us that we are part of a universe far stranger and more wonderful than we had ever imagined. The waves continue their journey across the cosmos, as they have for billions of years, carrying with them the memories of the universe's most dramatic moments. But now, for the first time in cosmic history, there are listeners scattered across a small planet, beings who have learned to detect these ancient whispers and to find in them new insights into the nature of existence itself. Tonight, as we continue our gentle drift through the cosmos of gravitational wave astronomy, let us turn our attention to something truly extraordinary that emerged from these ripples in space-time. For it wasn't just the detection itself that captivated the scientific world, but what these waves revealed about the fundamental nature of the universe and our place within it. Picture yourself standing at the edge of a vast, dark ocean on a perfectly still night. The water stretches endlessly before you, its surface mirror smooth beneath a canopy of stars. Now imagine that somewhere, far beyond the horizon, a great disturbance occurs. Perhaps two massive ships collide in the darkness, sending waves radiating outward in all directions. These waves travel across thousands of miles of open water, growing fainter with distance but never quite disappearing, until finally, hours later, they reach your feet as the gentlest of laps against the shore. This is not unlike what happens when we detect gravitational waves, except the ocean is space-time itself, and the disturbance is the collision of objects so massive and so distant that their very existence challenges our earthly intuitions about what is possible in the universe. Each gravitational wave detection tells us a story, not just about the specific event that created it, but about the broader tapestry of cosmic evolution. When we analyze the signal from a black hole merger, we're not just measuring masses and spins, we're reading the biography of objects that formed when the universe was young and strange, when the first generation of massive stars was just beginning to understand how to transform hydrogen into heavier elements through the alchemy of nuclear fusion. The black holes that merged to create the waves we detect today began their lives as stars dozens of times more massive than our Sun. These stellar giants burned bright and fast, consuming their nuclear fuel at prodigious rates, racing through their evolutionary stages in just a few million years rather than the billions that our more modest sun will enjoy. When these massive stars reached the end of their nuclear burning phases, they faced a moment of cosmic decision. Their cores, no longer supported by the outward pressure of fusion reactions, began to collapse under their own immense gravity. In some cases, this collapse would trigger a spectacular supernova explosion, blasting the star's outer layers into space and leaving behind a neutron star. But in others, the collapse would continue unabated, the stellar core shrinking past the point where even neutrons could resist the gravitational squeeze, creating a region of space-time so warped that nothing, not even light, could escape. These newborn black holes, scattered throughout the early universe, began a patient dance with their cosmic environment. Some remained solitary, invisible sentinels drifting through space with no electromagnetic signature to betray their presence. Others found themselves in binary systems, locked in gravitational partnerships with stellar companions that would shape their evolution over cosmic time. The binary black hole systems that eventually produce detectable gravitational waves represent the survivors of an extraordinarily complex evolutionary process. The two massive progenitor stars had to form close enough together to remain gravitationally bound, yet far enough apart to avoid merging prematurely. They had to navigate the treacherous phases of stellar evolution when one or both stars swelled to enormous sizes, potentially engulfing their companion or stripping away crucial mass through stellar winds. Many binary systems were torn apart during these phases, their components scattered across the galaxy to live out their remaining stellar lives in isolation. Others were disrupted when one of the stars exploded as a supernova, the asymmetric blast giving the newly formed compact object a powerful kick that could either tighten the orbit dramatically or break the binary apart entirely. The systems that survived these evolutionary hazards began a new phase of their existence, two black holes orbiting each other in the darkness of space, slowly losing energy to gravitational wave emission. This energy loss is incredibly gradual in the early phases, causing the orbital separation to shrink by just millimeters per year. But as the black holes draw closer together, the rate of energy loss increases and their orbital dance begins to accelerate. For millions or billions of years, these binary systems spiral inward at an almost imperceptible pace, their orbits shrinking so slowly that the change would be unnoticeable within a human lifetime. But gravitational waves are patient messengers, carrying away orbital energy with relentless precision, ensuring that the two black holes will eventually meet their cosmic destiny. In the final moments before merger, this stately progression transforms into something far more dramatic. As the black holes approach each other at significant fractions of the speed of light, their gravitational waves grow stronger and higher in frequency, creating the characteristic chirp signature that our detectors recognize. The space-time around the merging objects becomes a maelstrom of curvature, with tidal forces so strong they would stretch and compress any nearby matter in ways that defy comfortable description. The merger itself, when it finally occurs, represents one of the most violent events the universe can produce. In the space of a few milliseconds, two separate black holes become one, their event horizons touching and immediately snapping into a new, unified shape. The energy released in gravitational waves during these brief moments exceeds the total power output of all the stars in the observable universe combined. Yet for all this cosmic violence, the waves that reach us are incredibly gentle, stretching and compressing space by amounts so small they barely disturb the quantum fluctuations of the vacuum itself. It's as if the universe has learned to whisper its most dramatic stories, encoding tales of incredible power and destruction in the subtlest of cosmic murmurs. The detection of these whispers has opened up entirely new ways of studying the cosmos. For the first time, we can observe events that produce no light, no electromagnetic signature of any kind. We can peer directly into the hearts of processes that were previously hidden from us, watching as black holes collide and merge in regions where space-time itself becomes the dominant form of matter and energy. This new observational capability has revealed that the universe is far more dynamic than we had previously imagined. Black hole mergers, which were once thought to be exceedingly rare events, occur with surprising frequency throughout the cosmos. Every few days, somewhere in the observable universe, two black holes complete their billion-year courtship with a final, cataclysmic embrace. The properties of these merging systems have surprised astronomers with their diversity. Some involve black holes of nearly equal mass, creating symmetric collisions that ring space-time like a perfectly struck bell. Others are highly asymmetric, with one black hole significantly more massive than its companion, creating complex gravitational wave signatures that encode information about the unusual dynamics of these unequal partnerships. Perhaps most intriguingly, some of the detected black holes are more massive than stellar evolution theory had predicted possible. These intermediate mass objects, with masses dozens of times greater than our Sun, challenge our understanding of how massive stars live and die. They may represent the products of exotic stellar evolution pathways, or they could be the results of previous black hole mergers, hierarchical collisions, where the products of earlier mergers subsequently merge with other black holes to create ever more massive objects. The spins of these black holes also tell fascinating stories about their formation and evolution. Some rotate rapidly, close to the theoretical maximum allowed by Einstein's equations, suggesting they may have grown through accretion of matter that added both mass and angular momentum. Others spin slowly, indicating they may have formed through more direct stellar collapse or through mergers of black holes with randomly oriented spin axes. Each new detection adds another data point to our growing understanding of black hole populations throughout the universe. We're beginning to see patterns in the mass distribution, correlations between mass and spin, hints about the environments where these objects form and evolve. It's like assembling a vast jigsaw puzzle, with each gravitational wave event providing another piece of the picture. The neutron star mergers detected by gravitational wave observatories have proven equally revelatory, offering insights into the behavior of matter under conditions so extreme they cannot be replicated in any earthly laboratory. When two neutron stars spiral into each other, they create a gravitational wave signal similar to that of black hole mergers, but with some crucial differences that reveal the unique properties of these extraordinary objects. Neutron stars represent matter, compressed to the very edge of what physics allows. A typical neutron star contains about 1.4 times the mass of our Sun, compressed into a sphere just 20 kilometers across. The density at their centers exceeds that of atomic nuclei, creating conditions where the normal rules of chemistry and nuclear physics begin to break down. The equation of state of neutron star matter, the relationship between pressure and density in these extreme conditions, remains one of the great unsolved problems in physics. Laboratory experiments can probe nuclear matter at high densities, but they cannot replicate the sustained extreme conditions that exist in neutron star cores. Theoretical calculations suggest that exotic phases of matter may exist there, with quarks existing in configurations that don't occur anywhere else in the universe. Gravitational waves from neutron star mergers provide a unique window into this exotic physics. As the two stars approach each other, tidal forces begin to distort their shapes, causing them to deviate from perfect spheres. These distortions affect the gravitational wave signal in subtle but measurable ways, encoding information about how easily the neutron star material can be deformed. By analyzing these tidal signatures, physicists can constrain the neutron star equation of state, determining whether the matter in neutron star cores is relatively soft and easily compressed, or stiff and resistant to further compression. These measurements probe physics at the interface between nuclear physics and general relativity, where quantum mechanics and spacetime curvature interact in ways that push our theoretical understanding to its limits. The merger process itself creates conditions even more extreme than those found in individual neutron stars. When two neutron stars collide, they briefly create a hypermassive neutron star, an object that exceeds the normal mass limit for neutron star stability. This hypermassive remnant may survive for seconds or minutes before collapsing into a black hole, during which time it experiences conditions of temperature, density, and magnetic field strength that represent the most extreme physical environment in the present-day universe. The collision also ejects significant amounts of neutron-rich matter into space, creating the conditions necessary for rapid neutron capture processes that synthesize many of the heaviest elements in the periodic table. The optical observations that accompanied the first detected neutron star merger confirmed theoretical predictions about these R-process nucleosynthesis events, showing that neutron star collisions are indeed the primary cosmic sources of elements like gold, platinum, and uranium. This connection between gravitational wave astronomy and nuclear astrophysics represents one of the most beautiful aspects of the field. The same events that create the most dramatic distortions of space-time also serve as the universe's primary factories for creating the heavy elements that make rocky planets and complex chemistry possible. The gold in your jewelry, the rare earth elements in your electronics, were likely forged in neutron star collisions billions of years ago, scattered into space by the same processes that now send gravitational waves rippling across the cosmos. The multi-messenger observations of neutron star mergers have also provided new insights into the expansion rate of the universe itself. By combining the distance information encoded in gravitational wave signals with the recession velocity measured from optical spectroscopy, astronomers can calculate the Hubble constant, the parameter that describes how fast space itself is expanding. This gravitational wave approach to cosmology offers several advantages over traditional methods. It doesn't rely on the complex chain of distance measurements that has historically been used to map cosmic distances, avoiding many of the systematic uncertainties that have plagued previous determinations of the Hubble constant. Each neutron star merger, observed in both gravitational waves and light, provides an independent measurement of cosmic expansion, gradually building up a statistically robust sample. The early results from this approach have been tantalizing, suggesting that the expansion rate measured from gravitational wave standard sirens may help resolve a growing tension in cosmology. Different methods for measuring cosmic expansion have been giving slightly different answers, a discrepancy that has puzzled astronomers and may hint at new physics beyond our current understanding of the universe. As the catalogue of multi-messenger events continues to grow, gravitational wave cosmology promises to become an increasingly important tool for understanding the fundamental properties of our universe. Each new detection adds to our ability to measure cosmic distances independently, providing new tests of our cosmological models and new opportunities to search for unexpected physics. The technological achievements that have made these discoveries possible represent some of the most impressive feats of precision engineering in human history. The mirrors in gravitational wave detectors are suspended by systems so sophisticated they isolate the measurement from vibrations that would otherwise overwhelm the tiny signals from space. The laser systems maintain frequency stability that exceeds the precision of the best atomic clocks, while the data analysis systems search for patterns buried in noise using algorithms that push the boundaries of computational physics. Perhaps most remarkably, these instruments must operate continuously for months and years, maintaining their extraordinary sensitivity while the Earth rotates beneath them, while the seasons change. While human activity creates a constant background of vibrations and disturbances, they represent monuments to human patience and persistence, technological marvels that embody our determination to listen for the universe's faintest whispers. The global network of these detectors has created a new form of international collaboration, with scientists from dozens of countries working together to operate and improve these instruments. When a gravitational wave is detected, the information is shared immediately across the network, triggering coordinated follow-up observations and analysis efforts that span the globe. This collaborative spirit extends beyond the gravitational wave community itself, encompassing astronomers working across the electromagnetic spectrum, theorists developing new models of extreme astrophysics, and engineers pushing the boundaries of precision measurement. It represents science at its most cooperative and international, a reminder that our greatest achievements often emerge from working together toward common goals. The future of gravitational wave astronomy promises even more remarkable discoveries. As detector sensitivity continues to improve, we will be able to observe merger events from greater distances, effectively looking deeper into cosmic history to understand how black hole and neutron star populations have evolved over the age of the universe. Space-based gravitational wave detectors will open up entirely new frequency ranges, allowing us to observe supermassive black hole mergers at the centers of distant galaxies and potentially even primordial gravitational waves from the earliest moments of cosmic history. These future observations may reveal aspects of the universe that we cannot currently imagine, continuing the tradition of gravitational wave astronomy as a field that consistently surprises us with its discoveries. As you settle deeper into the gentle rhythm of this cosmic story tonight, consider the profound shift that gravitational wave astronomy represents in our relationship with the universe. We have gained not just a new observational tool, but a new sense with which to experience the cosmos, a way of feeling the universe's most violent events as they send ripples through the very fabric of reality. Each gravitational wave that passes through your body connects you directly to events of cosmic significance, to collisions between objects so massive and so distant that they challenge our earthly intuitions about what is possible. You are bathed constantly in these invisible waves, these whispers from the universe's most extreme corners, carrying stories of violence and beauty that span the breadth of space and the depth of time. The waves continue their ancient journeys across the cosmos, as they have for billions of years, as they will for billions more. But now, for the first time in the universe's long history, there are sensitive listeners scattered across a small planet, beings who have learned to detect these cosmic murmurs and to find in them new chapters in the endless story of existence itself. The story of gravitational waves draws us now toward its gentle conclusion, carrying with it a profound realization about the nature of discovery itself. As we drift through these final moments of our cosmic journey, let us reflect on what this achievement truly represents, not just for science, but for the human spirit and our endless quest to understand our place in the universe. There is something deeply moving about the fact that gravitational waves were predicted by pure thought, emerging from Einstein's mind through nothing more than mathematical reasoning and profound physical insight. No experiment guided his hand. No observation suggested their existence. They arose naturally from his equations, like poetry written in the language of spacetime itself, waiting patiently for a century until technology could finally catch up to imagination. This speaks to something beautiful about the relationship between theory and observation in science. Sometimes the universe reveals its secrets gradually, through careful measurement and incremental discovery. But occasionally, human insight leaps ahead, glimpsing truths about reality that lie far beyond our immediate ability to confirm. Einstein's gravitational waves were such a leap, a theoretical gift to future generations who would eventually develop the tools to hear what his equations had predicted. The century-long journey from prediction to detection reminds us that the most profound discoveries often require not just brilliance, but extraordinary patience. The scientists who dedicated their careers to building gravitational wave detectors worked on instruments they knew might never succeed in their lifetimes. They were driven by pure curiosity, by the desire to know whether these theoretical ripples were real, by the hope that future generations might benefit from their efforts, even if they themselves never heard the cosmic songs they were trying to detect. This kind of scientific patience has become increasingly rare in our modern world of rapid communication and instant gratification. Yet gravitational wave astronomy shows us that some truths about the universe can only be revealed through sustained effort across generations, through the accumulation of knowledge and technique that builds slowly, steadily, like sediment, gradually forming stone. The precision required for these detections also reveals something profound about human capability. When faced with measurements that seemed impossible, requiring sensitivity beyond anything previously achieved, scientists didn't simply accept limitations. Instead, they invented new technologies, developed novel techniques, pushed the boundaries of what precision measurement could accomplish. They created instruments so sensitive they could detect changes smaller than 1,000th the width of a proton, achieving precision that mocks our everyday intuitions about what it means to measure something. This extraordinary sensitivity opens philosophical questions about the nature of observation itself. At what point does measurement become so refined that it approaches the fundamental limits imposed by quantum mechanics? When we detect gravitational waves, are we observing classical distortions of space-time, or are we seeing the universe at the boundary where classical physics gives way to quantum uncertainty? These questions remain largely unanswered, but they suggest that gravitational wave astronomy may eventually push us toward new understanding of the deepest foundations of physical reality. The international cooperation required for gravitational wave astronomy also offers hope for humanity's future. In an age often marked by division and conflict, these projects demonstrate what becomes possible when nations work together toward common goals. The detectors themselves are operated by collaborations spanning dozens of countries, with data shared instantly across the globe and discoveries announced jointly by the entire community. This collaborative spirit extends to the rapid response networks that spring into action whenever a new gravitational wave is detected. Within seconds of a detection, alerts go out to observatories worldwide, triggering a coordinated dance of telescopes and instruments as astronomers race to capture any electromagnetic counterpart to the gravitational wave source. It's a beautiful example of scientific cooperation, showing how individual discoveries become richer and more meaningful when shared across the global community of researchers. Perhaps most importantly, gravitational wave astronomy has given us a new way of thinking about our connection to the cosmos. Each wave that passes through us carries information from events of unimaginable power and scale, connecting us directly to the most extreme phenomena in the universe. We are not just observers of cosmic events, but participants in them, our bodies gently stretched and compressed by ripples from colliding black holes billions of light years away. This connection is both humbling and elevating. Humbling because it reminds us of our tiny place in a universe filled with forces beyond our comprehension. Elevating because it shows that even from our small corner of space, we can detect and understand these cosmic events, transforming from passive recipients of gravitational waves into active listeners who can decode the messages they carry. The future of gravitational wave astronomy stretches before us with tantalizing possibilities. Each improvement in detector sensitivity will reveal new populations of sources, allowing us to map the gravitational wave sky with increasing detail and precision. Space-based detectors will open entirely new frequency ranges, giving us access to gravitational waves from supermassive black holes, and potentially even from the earliest moments of cosmic history. The possibility of detecting primordial gravitational waves remains one of the most exciting prospects in the field. These ancient ripples, if they exist and can be detected, would carry information from when the universe was less than a trillionth of a trillionth of a trillionth of a second old. They would provide direct evidence for cosmic inflation, offering insights into physics at energy scales that can never be reached by any earthly experiment. But even without these future discoveries, gravitational wave astronomy has already fundamentally changed our relationship with the universe. We have gained a new sense, a new way of experiencing cosmic events that complements and enriches our traditional observations of light and other electromagnetic radiation. We have learned to hear the universe singing to us in gravitational waves, and in doing so, we have opened a new chapter in the long story of human exploration and discovery. The gentle waves continue their journey across the cosmos tonight, as they have for billions of years, carrying with them the memories of the universe's most dramatic moments. Some waves now reaching us began their journey when the Earth was young and life was just beginning to explore the possibilities of complexity. Others started their cosmic voyage when the first stars were learning to fuse hydrogen into heavier elements, when galaxies were just beginning to take shape from the primordial smoothness left over from the Big Bang. Each wave that washes over us connects us to this vast cosmic history, reminding us that we are not separate from the universe, but intimately connected to it through the very fabric of spacetime itself. We exist within an ocean of gravitational waves, invisible ripples that carry stories from the most distant corners of space and time, and we have finally learned how to listen to their ancient songs. As you drift gently towards sleep tonight, carried along by these cosmic currents of discovery and wonder, remember that you are part of this extraordinary story. You live at a moment in cosmic history when humanity has just gained the ability to hear gravitational waves, when we are taking our first tentative steps into a new era of astronomical discovery. The waves that Einstein predicted in the quiet of his study have become humanity's newest window into the infinite. They carry us ever deeper into the mystery and beauty of the universe we call home, reminding us that there are always new songs to hear, new stories to discover, new wonders waiting just beyond the edge of our current understanding. Tonight, as the cosmos continues its ancient dance around us, as black holes spiral toward collision in distant galaxies and neutron stars prepare for their final embrace, the universe keeps singing to us in gravitational waves, and we, in our quiet corners of this vast cosmos, have learned to listen with instruments of impossible precision and hearts full of wonder, adding our own small voice to the symphony of discovery that defines the human experience. The gentle ripples in spacetime remind us that we are connected to everything, that the fabric of reality itself links us to the most distant stars and the most ancient events. In learning to detect these cosmic whispers, we have not just confirmed Einstein's century-old predictions, we have gained a new way of experiencing the universe, a new sense with which to explore the endless mystery and beauty that surrounds us always, even in the quietest moments of the night. Rest well, fellow traveller through space-time, knowing that even as you sleep, gravitational waves continue their patient journey across the cosmos, carrying with them the songs of the universe itself, waiting for curious minds and sensitive instruments to decode their ancient messages and find in them new chapters in the eternal story of existence.